Hey, hello everybody, this is Pro123 again, and today we're gonna be learning Cipher method in order to decipher what is written here. It is Cipher in ciphering method, so we're gonna apply it to actually get what is written here. It is actually a problem from April Fool's Days contest in Codeforces. I'm leaving you the link to the problem in the description. I am also giving you the link to the Cipher method, which we have right here. Okay, so first we're gonna examine how to apply Cipher decipher to this paragraph that we have here. So first we're gonna read the whole paragraph and we're gonna explain the meaning of this line later, but well, let's read all the paragraph. Now that we have this paragraph with this method sim.end of file, we are gonna be applying 26 times the Cipher ciphering method, and we are gonna get a list of the possible decipherings, and we're gonna take a look at each of those decipherings, and that is how we are going to determine which decipher is the good one. Okay, now that we have already explained our main function, let us go to Cipher deciphering method. It is gonna be a function that is gonna return a string, and well, this is the number of times that we are gonna move our string either to the right or to the left. Okay, we get the size of the string, and we are going to run a for loop over the whole string, and if that is not a lowercase letter, let's ignore it. Let's move on. And if it is a lowercase Latin letter, then we are going to apply the shift of that letter either to the left or to the right according to this letter t, this variable t. So you may be asking, why am I subtracting letter A and then adding letter A again? Well, the thing is that letter A, which is like 65, or no, it's like 91 in ASCII, is not actually 0 in modulo 26. So for us to get the true value of this guy over here in modulo 26, we have to subtract A to get the true value of this in modulo 26, and then we add A again to obtain a lowercase Latin letter in the ASCII value, and then we subtract A and add T, which is the number of chips, and get modulo 26 again, and add A, of course, and then we return the modified string. And now we're gonna run from 1 to 26. Well, actually applying 26 chips is like doing nothing, so we're gonna iterate from 1 to 25. That's better. Okay, so for this problem we can do this, or we can find a Cipher deciphering method on Google, but we have more fun programming this deciphering method. Okay, so let's apply this. We're gonna compile our code. Now we run it. Okay, we're gonna add the input from this file, and we're gonna print it to this other file. Okay, so Cipher in, and we print it to Cipher out. Okay, now what is written here on Cipher out? Well, a lot of lines, but each of these numbers is going to be a deciphering, one of the possible decipherings. Okay, so number 2, well, we don't see non-words. It's until number 10 that we see non-words, is a prime number whose reverse is a different prime number. Okay, so it's actually 10 chips that we have to apply. Okay, so instead of printing the 26 possible deciphers, we're gonna print just the one that we care about. Okay, sorry for that. It's actually one line comment, and we're gonna apply just 10 chips. Okay. Oh, sorry. And now we have only this line, but this is a little bit messed up, so that's why we need this line. We're gonna add an end line character when we get every line from the input. Okay, now let's apply the deciphering again, and now we have the problem written in a beautiful way. Okay, so the problem says that an emirp is a prime number whose reverse is a different prime number. Your task is to find the nth emirp. In the input, we are gonna have the single integer n, which is gonna be at most 11,184, which is the one base index of the emirp to find, and we're gonna output a single number, which is the nth emirp. Okay, so this is the Cipher deciphering method, and now we're gonna move on to the solution of this problem. For this problem, we're gonna need the prime function, the is prime function. It should be named is prime, but for simplicity, we're gonna call it just prime function. Okay, we're gonna need that function and the function reverse. We can do this function in line, but I'd rather do it outside the main function. Okay, this problem can be done with brute force, and no problem with that, because we are gonna be examining at most like 10 to the power of 5 numbers, I think. I don't remember exactly, but we can just iterate over every possible I from 11 to get the nth emirp. We're not gonna run out of time if we run a loop from the first to the nth emirp. Okay, so we can actually apply brute force in this problem. We don't need any fancy technique. So what we're going to do is to read n, and then we're gonna declare this variable counter, which is gonna be augmenting when we find another emirp number, and this variable I, which is the number that we're currently examining. Okay, so if I is prime, we're gonna move on, and we're gonna get the reverse number of I. So to reverse I, what we're gonna do is that we are gonna get the modulo of that number. We're gonna divide that number by div. As you can see, div is going to be multiplying itself times 10 times 10. So we're gonna actually get our digits in order. This is how we reverse this number, and we return the reverse value. Okay, we store that reverse value, and we ask first if that number is different from I. Of course, 11 is a palindrome, so it is not going to count. So we can actually examine from 13, but let's leave it as 11. Okay, so we examine first if they are different, and then if that reverse number is also prime. If those two conditions are fulfilled, then we augment our variable count, and if this is equal to n, if count is equal to n, we're gonna print that number, which is the one that we care about. And if I is prime or not, we have to increase the value of I. So basically that is the code for this problem. Let us compile. So we're gonna find the first emirp, and we're gonna find the first emirp, which is 13. Let's find the second one, which is 17, because if we reverse it, it is 71, and 71 is also a prime. Now that is everything we have to do. This code that I just showed actually gets accepted. What we have to learn from this video is this prime function. In this prime function is not complete because we don't need a complete prime function in this problem, but to make it more accurate, we can actually ask first if that number is equal to 1 or it is equal to 0, then it is not prime. Now if that number is equal to 2, return true, and that is the complete function. Okay, to verify if a number is prime in square root of n time complexity. Okay, so as you can see, when I times I is greater than n, then we don't check any more numbers because we know that this number is prime, and we just return true. Okay, that is the prime function. That is the function to verify if a number is prime in square root of n steps. Okay, basically what we are doing is that we start from 3 and we iterate over all odd numbers because we have already checked all even numbers, and if every number, and if in neither of those odd numbers n modulo I was equal to 0, then it is going to be a prime number, else it's gonna be false. Okay, if it is not going to prime, it is not going to be prime. So that's everything for today, you guys. I hope you enjoyed this video. Share it with those who need it. Remember, what we learned in this video is Cipher deciphering method and prime checking in square root of n steps and reversing of a number. That's basically what we did today. Remember, the original problem, well, the original problem was this one, and the deciphered problem is this one. Okay, I hope you enjoyed this video. Remember to subscribe, and bye bye.